So compressed system typically, providing up around 10 to 13% efficiency in total. Most of the energy is going into waste heat, which is the cooling circuit. The areas which are colder, the heat recovery from this system also becomes feasible. But if we are living in hot areas, the heat recovery might not bring in so many fruits. So in colder areas, we have a typical return on investment of about 1 year. In hot areas or warm areas, the payback might be around 2 years. We need to have standby cooling towers with this as well, obviously, but these will only be standby. The main cooling needs to be done by the heat recovery system. This recovered heat can be used to heat up water as well as heat up air. If we have a boiler or a air or a thermal oil heater nearby, we could directly heat up their intake air using this air. Or if we don't have it, we could heat up water and then you feed this water to boiler or other processes. But critical aspect would be if we have a big system or a small system. If we have a small system, it might not give us useful amount of energy, but if we have a multi-compressor system or large compressors like we usually have in weaving and spinning, there we can gain a lot of energy. The problem is where to use that energy. So if we have an integrated system where we have spinning, weaving, and thermal wet processes as well, that is where this becomes feasible. So we recover heat from here, feed this heat to the boilers or thermal oil heaters or the processes, so we can do some of the recovery. So key questions in this case would be, what is compressed air used for? Why are we using compressed air? As we saw in earlier, for this fabric cleaning process, do we even need to use compressed air or not? Can we use something else? And why is it necessary? So asking this question is very important. Then talking about load profile, if we automate the compressors, if we have multi-compressor systems, these may result in 30 to 50% energy savings typically, because multi-compressor systems are not controlled very well only by pressure modulation, but we need to have an intelligent control system there with VFDs as well. Do you see this chart? As you can see, the moment compressor K1 goes off load, the compressor K4 goes on load. And the moment compressor K1 reaches its maximum load, the K4 goes into offload position. But the main issue here is that the moment this K1 goes into offload position, the K4 starts kicking in. But as soon as K4 is there at its peak, K1 starts to kick in and K4 has to go down. So you can see that K1 is going into reasonable load here, then going off load, but K4 is only going into load for only a fraction of time and then going off load. There is actually a problem of sequencing between K1 and K4. If K1 stays in load, K4 might not need to kick in. So this is where we can, if we plot them all together into one line, that is where we can see what is happening simultaneously between these. Then this single compressor system, as you can see, it is only going on load shortly, then going off load, on load, off load. This seems to be an oversized compressor whose demand is very low, and it's just going into on load and off load. So all this offload time, it's only consuming energy but not really contributing to it. A typical case where a variable frequency drive can be installed, and we can easily modulate this one because it's a single compressor system. Then another one, as you can see, the green one and the red one, they are usually kicking in together and going offload together, staying offload, then kicking in together and going. So they are synchronized in terms of starting and stopping. Do you think there's any improvement potential here?
So for this chart, I think it is a waste of energy since two compressor is on load and offload at the same time.
Yeah,
So I think that there is a loss on the offload. So I think that is a waste of energy.
yeah.
They on load at the same time. So to reduce the energy loss, we will control one will be on full load and one will be just on normal load, so they don't, conflict with each other.
Great. And then the leakages, everybody is aware of the leakages, that we need to control the leakages. This is a typical leakage test when there was no demand and only the compressor was running. So this is the load profile of the compressor. After in the beginning, when it fills in all the reservoirs and pipes, it should ideally go into offload condition for a very long time. But this was continuously going on load and offload. So a lot of saving can be done here. Then the pressure drop study, one of you also mentioned earlier that we do a pressure drop study and see where we are receiving a pressure drop. This kind of a study would also help us in identifying in which area we need to provide a receiver tank, an additional receiver tank, or improve the pressure provision. Then talking about dryers, we usually try to keep the dew point of the final discharge compressed there between 3 to 5 degrees Celsius. For this, we need to have a dew point sensor. So we try to keep it between 3 and 5% to avoid condensation. If we go too low, nearing zero or in minus, that means that we are over drying. If we go above 5 degrees, that means we are under drying and then a condensation will take place. This condensation not only takes place because of the temperature, but also because of the friction in pipes. So this setting where we had 6 dryers. So dew point at main discharge was 1.5 degrees Celsius. And then you can see the values of each of the dryers. Top 3 dryers were over drying, or let's say dryer 1 and 2 were over drying, dryer 3 was working fine, and 4, 5, and 6 were under drying. So they was not working properly. We got them repaired, and then we requested factory to maintain this between 3 and 5 degrees Celsius. So same amount of compressed air with full load. Now they are only running first 4 dryers, and remaining 2 dryers are totally on standby. All they had to do was install some humidity sensors, install a dew point sensor in the main line, and typical payback for this sensors is less than 1 year, actually, even half a year. So this was a good study and that we did, and I think this is something, if you have a dew point sensor, we can always do an optimization of the dryer processes. This is only rarely that we see the factories over drying. In most of the cases, we see that the dew point is between 30, 35 degrees Celsius, and we see a lot of condensation and pressure drops. So if we keep the dew point below these 5 degrees Celsius, the pressure drops would also reduce. Then cooling towers, there we need to monitor the heat exchange that is being done in the cooling tower, how much range we are getting, that is the delta T it is producing, what temperature is water is entering the cooling tower and what temperature is going out. Then if we can do an automated control based on temperature sensors, that actually brings in a lot of savings, because the temperature varies whole day during 24 hours. It also varies among the seasons, and also there is a lot of variation in the cooling demand. So for example, sometimes there's one compressor running, sometimes there are 2 compressors running, sometimes the compressors are on load, sometimes they're off load. So the cooling demand varies. If we have an automated system with the VFD installed on pumps and fans, we can typically get a return on investment in less than 3 years. If we have bigger system, the payback is quicker. In the bottom, I show you the range values that we measured in 4 cooling towers, you can see the cooling tower 1 and 2 were not providing enough cooling. So the delta T there was only around 7 degrees Celsius. Cooling tower number 5 and 6 were around 9 degrees Celsius. Ideally, they should be around 10 degrees Celsius. And we saw that in number 1 and number 2, these cooling tower fins were clogged, and the distribution of water droplets that are falling was also not even. That was causing the low range. So we got them, these cooling towers fixed, did some maintenance, and they started working pretty fine. Water quality is also important. If we are using soft water to make up water levels, or what kind of water we are using. If we use soft water, then we have low scaling of fills and better heat exchanges achieved. Obviously, the water pumping cost decreases in this case, and water treatment cost also would decrease if we have better systems. Then pumps and pumps average, if you do an overall analysis of efficiency, we find pumps far less efficient, 40%, 30%, 25%. This one graph in the bottom shows a pump running at a low power factor because it's a large pump and the demand is low. And these are kind of pumps where we can explore the possibility of installing variable frequency drives, and we can also do a pump efficiency analysis where we, even using this Meyer tool, for example, if you use the Meyer tool, it allows you to calculate the losses in the pump system. So it calculates different kind of losses that can be there. So I recommend that you use Meyer system for pumps as well. Typical issues to consider in pump selection is to select the right size of pump based on the net suction head. And the pump type is also very, very important depending on what kind of requirement do we have. Do we want to have an axial flow, a centrifugal flow pump? And then compatibility with the variable speed drives is important. Some pumps are not compatible with VFDs because these are old technology pumps. We often see that pumps do not have plate type readings. So we are not even able to see what is the rating of this pump. And because of that, we once did a calculation of the efficiency. And since the ratings that were provided to us by the factory team were wrong, the efficiency came out to be more than 100%. So that already means that the data that was provided was wrong. So we had to, skip that data. So it's important that all the motors and pumps should have the type plate readings. If they don't have type plate readings, there's no use doing the audits of these pumps or motors because we don't have the real data. Then system resistance. So just like compressed there, we have pressure drop issues here as well, and pressure and resistance issues here as well. So the piping friction needs to be reduced based on using less number of bands, improving the pipe material quality, or improving the or controlling the friction for the corrosion, for example. Then plant designing. So matching the pump usage with the demand side. So if we need less water, we should modulate pumps just like we modulate compressed air systems as well. We can also modulate pumps as well. Yeah, then water balance analysis would also provide us where the whole water is coming in. Sometimes we've seen that companies use dampers and they use bypass lines. So if the water is not required in the demand side, they bypass the line, the water goes back to the suction tank, which is a total loss of efficiency. Instead, there should be variable frequency drives installed. So variable frequency drives are pretty much more than 50% of the times these work. Recently, we saw a case where the factory even skipped some pumps. So they did the schematic diagramming of all the pumping circuits, and they figured out that they have too many tanks in between. So they pump the water from one area to another area, then they have a tank, then they pump it again, then another tank, and then they pump it again. So what they did was They did some sequencing, some piping redesign, and removed the tanks in the middle. They kept only one tank that was needed for the demand side. This way, they were able to remove two pumps from the line. So rather than running three pumps, they were running only one pump, and that too was equipped with variable frequency drive. So they saved a lot of energy in pumping. If we need high pressure in some areas, we could use booster pumps in those areas rather than increasing the pressure of the whole system. And then maintenance is something that we also need to take care of. Monitor the temperature of the pumps, vibration, noise, monitor the knocking in the piping system, for example, and see how it is performing and in which areas we are getting more knocking. If there is air trapping, for example, in the pipes, do we have proper air vents installed or not? If there are any leakages. So we found out that the seal of a pump was leaking, and this pump was actually transmitting chemicals. So when and the seal was leaking only drop by drop, but this drop by drop, when we collected it, measured the time flow of this leakage, this was in hundreds of dollars amount per month, because it was chemical, not only water. So these leakages and these systems also are very much relevant in pumps as well. Then we come to chillers, pretty much same way as we control pumps or we control compressed air systems. These are just the medium is different for these equipment. The way of operation is same. We do need to do the sequencing. We need to match these with the demand side requirement. Chillers are usually used in processes for cooling down the process water. Some dyes need to be prepared in chilled water. There are some machines that need to be cooled down by chillers, and sometimes the space cooling, for example, in weaving or in spinning, we need to use this cooling for the ventilation, cooling air conditioning system. The question typical to ask in the factory is, why are we doing the chilling? Do we really need it? Do we really need to? Why do we have an electrical chiller, and why don't we have an absorption chiller? And is there a demand for it? For example, what are the temperatures required? If the temperature required is around 25 or 30 degrees Celsius, why are we even using a chiller? Why are we not using a cooling tower? Because that temperature can be achieved by good cooling towers as well. And then, do the demands vary or not? So if the temperature demand on the demand side varies, are we modulating the chillers accordingly or not? So these are typical issues. The refrigerant leakage is a big issue. If we have a refrigerant type, which is not a brine solution, not a water system, but we have a gas refrigerant, these have huge global warming potentials. There are some refrigerants, if 1 kilogram of that refrigerant leaks, it is equal to 20,000 kilograms of CO2 emitted. So the global warming potential for refrigerants is so high. Some are persistent in terms as well. So those which are persistent, they stay in the environment for very, very long time. They don't just dissipate. So there's a big energy loss when the refrigerant is leaked, because we have to fill the refrigerator again. We have financial loss, but very huge GHG emissions. It is important to continuously monitor the refrigerant pressure to ensure that there is zero leakage. Also, we should consider switching to refrigerants which have low GWP compared to those which we are currently using. So I saw recently a factory was using brine solution as the main system. So this brine solution does not have any global warming potential, which was a good case study for me. So this is all about this. And then heat exchangers, obviously, when we're using heat exchangers for the chilled water, we also have to look for the condensing that is taking place in the heat exchange. If the condenser water flow reduces, that means that heat exchanger has started clogging, and 20% reduction in condenser water flow would mean 5% increase in energy demand. So this is an important parameter to look forward in the in these chillers as well. Then we come to fans. So this is a typical fan duct system that is provided by this Meyer tool, where we have fan input, then we have multiple dampers, we have this fan and the motor, then we have dampers in the outlet as well. So the question is modulation required, or is it a continuous flow system? If modulation is required, are we using dampers or are we using variable frequency drives? There are some industrial fans whose blades also have variable angles. You can set blade angle as well. If the demand varies constantly for number of days, for example, these kind of blades are used in the weaving and spinning ventilation systems usually, where we have variable speed, variable angle blades. So we change the angle to change the flow rate. But best way is to use a variable frequency drive, measure the requirement on the demand side and modulate the VFD and motor accordingly. So example assessment provided by Meyer is, for example, a baseline condition. This was an example assessment done in Meyer that baseline condition was that the usable output provided by the fan was 66.6%. And for a scenario where they optimized the fan and motor combination, the useful output increased and fan losses reduced. And when they reduced the pressure and flow, the useful output was still better than the useful output of the baseline conditions, and fan losses were also lower than the baseline conditions. So these are kind of assessment you can also do directly in Meyer. I highly recommend using Meyer for the next audits that you do.